Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you, and today we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
So here is our sixth NMR challenge. We are going to determine the structure of this organic compound having molecular formula C6H4Br2 from the given NMR spectra. So while determining the structure of this organic compound, we are going to follow all those steps which we learned in the last videos. So first we will calculate the index of hydrogen deficiency, then we will look 1H NMR, and after that we will look 13C APT NMR. Before solving this problem, we are going to revise all those steps which we are learning since beginning, and we will revise chemical shift value for 1H NMR and 13C carbon NMR as well. This is very important to keep revising because this practice will make you perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problem. And 1H NMR chemical shift values is also very important to understand shielding and deshielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly deshielded as compared to the primary, and tertiary hydrogens are slightly more deshielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly deshielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, So it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. So now we are ready to take this challenge. So first we will calculate the index of hydrogen deficiency. 2C plus 2 plus number of nitrogen minus number of hydrogen minus number of halogen divided by 2. 2 multiplied by 6 plus 2 plus 0 nitrogen minus 4 hydrogen minus 2 halogen divided by 2. So it has 4 degree of unsaturation. So it may be belongs to benzene ring. If it belongs to the benzene ring, then NMR must show the signal in the aromatic regions. So let's look. So 7.36 ppm signal indicates that this compound has benzene ring. So the 4 degree is goes to the benzene ring. Now look at the 1H NMR more carefully. So it has one signal, which means that it has only one type of proton or hydrogens, and the signal at 7.36 ppm is singlet corresponding to the 4 hydrogens. So it means in the neighbor there is no hydrogen or equivalent hydrogen, and this 4 hydrogen means that the benzene ring is disubstituted, and it also indicates that this benzene ring has plane of symmetry. Because it has only one signal, it means this compound has plane of symmetry. So now we have following information. This compound has benzene ring, so 6 carbons goes to this benzene ring plus 4 hydrogens and plus 2 halogens. So we have to arrange 2 halogens on this ring in such a way that it must show only one type of hydrogens. So let's try to do it. So first possibility is that this bromo are ortho to each other. So in this case, you will have 2 types of hydrogens. One is this type of hydrogen, another is this type of hydrogen. So hence this could not be the correct structure of this compound. Let's look at the other possibility. In this case, if we put at the meta position, then it is also not possible, because this hydrogen will be one type, this and this will be same type B, and this will be C type. So 3 types of hydrogens are there, 3 types of hydrogens. So this is also not the correct structure. Now look at this option in which bromo are present at the para position. So if you draw the plane of symmetry, then this hydrogen and this hydrogen have same chemical environment. This hydrogen and this hydrogen also have same chemical environment. So all these hydrogen are same, so it has only one type of hydrogen and it will show only one signal. So hence we can say that the correct structure for the given NMR belongs to this compound. Oh wow, we managed to determine the structure of the compound just by looking the 1H NMR. Okay, but we can use this carbon NMR information to verify our structure one more time. So this compound must show 2 types of carbon signal, one for this one, which should be quaternary carbon, and another for this CH, which should be in the negative phase and in the aromatic regions. So if you see that we have only two signals, one is this one and one is this one. So this signal belongs to CH because it is in the downward side, and this one belongs to the carbon attached to the bromo. So we can easily say that this carbon NMR belongs to this compound. So unequivocally we can state that this is the correct structure for the given NMR spectra. So now here is the challenge for you. So this is the NMR spectra for the C4H8Cl2. So try to follow all those steps and determine the structure for this compound, and I will disclose this in the next video. So don't forget to subscribe my channel. We will see you in the next video. Thank you very much. Take care. Bye bye.